Okay, so I mentioned this term before, cosmology. Cosmology is basically, what does the universe look like? What's around us, what makes up the universe, how is it distributed? And in particular, in antiquity, observers, look at the night sky and try to explain certain things. They try to explain the sun, the motion of the sun, the motion of the moon, the motion of the planets, and the motion of the stars. And so someone asking, what does our local universe look like? And a lot of different cultures, approach this in different ways. Many made maps of the stars, ways to understand or to predict how the stars, how the sun, how the moon will change over time. The motions of the sun are very important when it comes to when you want to plant your crops, when you want to harvest your crops. And so there's a lot of practical reasons to want to understand what the sun is doing over time. At the same time, understanding what the moon is doing, what the planets are doing, what the stars are doing, helps build a picture of what the universe looks like beyond the Earth. So I'm just going to go through 4 basic observations that, again, made by lots of different cultures. We have recordings from the Greeks, written records from the Greeks, but a lot of cultures, made these same 4 basic observations. Okay, so number 1, the sun, the moon, most of the stars, and the planets all follow the same path through the sky. They're going to rise from the eastern horizon, they're going to go high in the sky, and they're going to set on the western horizon. And it takes them about 24 hours to make a full cycle. If you see a star high in the sky, you wait a few hours, it'll set on the western horizon, and about 24 hours later, it'll be roughly in the same place, high in the sky again. Okay, so every object, sun, moon, stars, planets, all follow that same basic motion. Number 2, the sun doesn't quite follow the same motion as the stars. It changes respect to changes position with respect to the background stars a little bit each day. And in particular, it takes a year to complete a full cycle. So you can't see the sun and the stars at the same time, but if you take detailed observations, you can infer what stars would be behind the sun if you could see those stars and the sun at the same time. And essentially the sun moves through different constellations from night to night to night. Or rather day to day to day in this case, because we're seeing the sun. And so one day the sun will be in the constellation of Leo, some other time of the year it will be in the constellation of Capricorn, and it takes a full year for it to get back to Leo. Very important to people who rely on agriculture is the highest point the sun reaches that will change over the year. So during the summer, the sun will be very, very high in the sky and lower during winter. Here in Las Cruces, the sun never actually gets directly overhead, but it gets somewhat close. During winter, the sun is close. It gets the highest point is a little bit closer to the horizon compared to the point directly overhead. The moon goes through its own motions as well. It's going to change. It moves with respect to the background stars. If you come and look at what stars are behind the moon one night, and then come back the next night, the moon has moved across quite a few constellations. The moon also changes shape, it changes phases, and the cycle for moving through the stars and changing phase is about once a month. And the planets, they have their own very peculiar motions as well, which we'll talk about in great detail now. And essentially, understanding the planets has been something that astronomers have struggled to do for hundreds of years. Really thousands of years to really get a complete picture of why planets move the way they do. So first of all, where does the word planet come from? It's basically the Greek word for wanderers, because unlike the other stars, there are certain objects in the sky that move somewhat differently from the other planets, from the other stars. And so those planets move differently from the stars. So for the most part, planets like the sun, like the moon, like stars, follow the same basic pattern. Rise in the east, go high in the sky, set in the west. But on top of that, there's a little bit of extra night-to-night motion. And mostly, planets move west to east. They move eastward. So just like the sun and the moon, they move a little bit more eastward each night. So if you come out and find Mars, come out the next night and find Mars again the night after, it's a little bit more eastward each time, except when it goes the opposite direction. Sometimes you come out the next night and it's not a little bit more east, it's a little bit more west. It changed directions. and then it changes directions again and goes the opposite direction. So let's take a look at this figure here. So this is the result of a photographer basically taking about 20 or 30 images over the course of several months, constantly pointing towards the same set of stars in the background, and just laying those images on top of each other. And so the background stars, they all line up nicely. They're all in the same position. The stars are not moving with respect to each other. This star is always here in the image. The star is always here in the image. But the location of Mars is changing from night to night to night. In June, Mars is over here. As we come through June through July, Mars again is moving eastward. On this figure, east is to the left, north is up. So Mars is moving eastward from June to July. From August to September, Mars stops, changes directions, and moves towards the west. And then at the end of September, it stops, changes directions again, and moves towards the east as well, one more time. So again, mainly moving eastward, turns around, starts going towards the west, turns around again, starts going eastward. And this is, one more time, this is the night-to-night motion. On a single night, you'll see Mars doing what all the other stars do, rises in the east, sets in the west. But if you come night to night to night, the stars that are behind Mars are changing in this, again, strange pattern of moving in one direction, stopping, moving in the opposite direction, and then moving in the first direction again. And this motion is called retrograde motion. This reversal of motion that you see for the planets that you don't see for the other stars. Okay, so we're going to talk a little bit about how the Greeks made sense of this strange motion of the planets. First, just want to sort of talk about the good and the bad of how the Greeks approached natural observations. And the good, and this all traces back to Thales, three important principles here. There should be natural but not supernatural explanations for things we observe. So don't invoke Zeus for everything you want to explain. See if you can find a natural explanation for why something happened. Number two, mathematics are the key. That with advanced mathematics, you can explain the world we see around us. You can explain what's happening. You can make predictions for what the future will hold. You can know where Mars will be 3 years from now by making careful mathematical models, careful mathematical calculations based on the observations you've made. And again, most importantly of all, if an explanation contradicts what we observe, that explanation is wrong. An explanation is only as good as it explains the observations we make. That the ultimate test of which hypothesis is correct is the one that best explains the observations. And the Greeks weren't perfect. There are a couple of not so good traditions that were in Greek, that were sort of embedded in Greek thought that stopped the process of science from going quite as far as it could. Number one was this very strong belief in reasoning first, observing second, that the correct answers always came from within the mind. So as opposed to making observations and then thinking how you'd explain those observations, you first stop, you close your eyes, you thought about what the universe should be, and then you went out and looked for observations to confirm that. The second point is a belief that the heaven should be perfect. So heavens are just basically anything that's not Earth, and that the heavens should have perfection. And perfection was defined in a very specific human way. Perfection meant not changing. The stars in the sky should be exactly the same tonight as they are tomorrow night, as they are a year from now, as they are 1,000 years from now. That nothing changes in the heavens because the heavens are perfect and unchanging. And number two was the belief that there are certain geometrical shapes that are more perfect than others. In particular, circles and spheres were the most perfect shape that the Greeks could imagine. And therefore, all motions had to be on circles because circles were perfect, the heavens were perfect, and therefore heavenly bodies must move on circles. And again, these preconceived notions of what things should be started to infect how they looked at how they interpreted their observations, how they made sense of the universe around them. Okay, so this brings us to the model that sort of guided a lot of science for hundreds of years after the Greeks made their observations. This thing that we call the geocentric model. The geocentric model was first proposed in Greek thought about 2,600 years ago by Anaximander. And it had these basic components here. So the idea is the Earth is at the center, the Earth is not moving, the Earth is not rotating, the Earth is perfectly fixed at the center of the universe. And all of the stars we see are embedded or encrusted on this thing we call the celestial sphere. It's a sphere. So again, here's the Earth at the center, and then all around the Earth is this big celestial sphere with all the constellations we see in the night sky encrusted, embedded in the celestial sphere. The sphere has a north celestial pole above Earth's north pole, a south celestial pole above Earth's south pole, a celestial equator above Earth's equator, and the sphere rotates roughly once every 24 hours. If you're being a stickler, it's once every 23 hours, 56 minutes, but roughly once every 24 hours. On top of that, so again, Earth is not moving, Earth is fixed. The celestial sphere rotates around the Earth, which is why we see the stars rise in the east, go high in the sky, and set in the west. On top of the celestial sphere is a circle called the ecliptic. It's not exactly along the celestial equator, but it's close. And this ecliptic is where the sun moves, where the moon moves, where the planets move. Anytime you look for the planet Mars, it's somewhere along the ecliptic. And again, the rate at which these different objects move changes. So once a year for the sun, once every 30 days for the moon, and different rates for the planets to come back to where they were before. And just to be very clear, this is not an accurate model of how the universe works. The Earth does in fact move. The sun does not orbit the Earth orbits the sun. But that said, as a mathematical model, this actually makes pretty good predictions for where the stars are. It makes such good predictions for where the stars are that telescopes today still use this geocentric model just to predict where a star will be on a given night. If I want to look at the star 51 Eridani 3 nights from now, the telescope will use this celestial sphere model to figure out where on the horizon the telescope should point. How far above the horizon and to what azimuth the telescope should point to find the star 51 Eridani. So again, a incorrect physical model, but one that makes good predictions. All right.